Hi everyone, in today's Fundamental Skill Builder series on the subject of organic chemistry, I'll be teaching you on locating partial charges resulting from induction. So I'm going to give a brief lecture on electronegativity and the types of class bonds we organic chemists generally classified as. So electronegativity is defined as how much an atom wants the electrons. So the higher the electronegativity, the more the atom wants to gain the electrons. And in general, it's going to increase from left to right across the period and from bottom to top across the group. There's three types of bonds we organic chemists like to classify. It's either as first, nonpolar covalent, second, polar covalent, and third, ionic. And we're going to measure to classify the bonds between two atoms based on the difference in electronegativity. So if the electronegativity difference is very small, which I like to say less than 0.5, then the bond can be classified as nonpolar covalent. And examples include carbon-carbon and carbon-hydrogen. Now, when the electronegativity difference is semi-high, which is about 0.5 to 1.7, we classify this kind of bond as polar covalent. And examples include nitrogen-hydrogen, carbon-oxygen, or even carbon-nitrogen. So I wrote here that lithium-carbon, this is the difference between lithium and carbon is about 1.5. So it's a little bit, we can classify either as polar covalent or ionic. Either one will be okay. And if the electronegativity difference is very high, which is greater than 1.7, we will classify the bond as purely electrostatic attractions. And examples include lithium nitrogen or sodium chloride. So in today's walkthrough, we're going to identify all polar covalent bonds and show any partial charges that result from inductive effects in this molecule called methanol. And to walk this through, there are generally three steps I like to follow. First, we're going to identify all the polar covalent bonds in the molecule. So the only ones in here are carbon and oxygen and oxygen and hydrogen. In the second step, we're going to determine the direction of each dipole. Remember, the tip of the arrow, or the arrowhead, is going to point towards the more electronegative atom, while the end of the arrow, which has a plus at the end, is going to point towards the more electropositive or the less electronegative atom. So in both of our dipoles, the tips of the arrows are going towards the oxygen, away from carbon and hydrogen. In the last step, we're going to indicate the location of the partial charges. So the more electronegative atoms is going to get what's called a delta negative sign, and the more less electronegative atoms are going to get the delta positive signs. And the delta negative, delta positive sort of indicates whether the atom is electron rich or electron poor. So in today's exercises, we're going to identify any polar covalent bonds by drawing delta positive and delta negative symbols in the appropriate locations using the walkthrough that I presented earlier. I'm going to work from top to left and from top to bottom. So starting from the top right to the lower to the top left to the lower right. In this first example, we see this very long chain ether functional group molecule. And for first thing, we're going to look at determine all the polar covalent bonds. So all the polar covalent bonds are here, if you remember from the lecture. So therefore, now we can draw the appropriate dipoles resulting from these polar covalent bonds. And we have going from carbon to oxygen, carbon to oxygen, carbon to oxygen, and carbon to oxygen again. So therefore, both oxygens are going to have a delta negative sign, and all of the carbons are going to be electron deficient, and they will have the delta positive sign. So the correct answer to this question is delta positive here, delta negative, delta positive, delta positive, delta negative, and delta positive. Sorry, my delta, this last one looks like an 8. It should look like this. There we go. All right, on to the next one. Here we have this molecule called chlorofluoromethane. And first, we're going to identify all of the polar covalent bonds. So we have this one and this one. And then now we're going to determine the direction of the dipole from these two bonds. Remember, fluorine is more electronegative than carbon, so is chlorine. So the dipoles are going to go away from the carbon atom. And therefore, we're going to assign the delta signs that carbon as electron deficient has a delta positive sign, and both fluorine and chlorine are going to be delta negative. Now, the effect due to fluorine is going to be greater than the chlorine because fluorine is more electronegative than chlorine. That's a side note. Here, we have this reagent called, you will learn later on organic chemistry, called the Grignard reagent. So here we have, to identify all of the polar covalent bonds. Now carbon and magnesium is going to be polar covalent, and so is magnesium and bromine. Now remember who is more electronegative than the other. Carbon versus bromine. Carbon is actually more electronegative than magnesium. So therefore the dipole moment is going to go from magnesium to carbon. So carbon here actually will act, later on we'll call this as a nucleophile. And the direction of the dipole between magnesium and bromine is going to go towards this way. So bromine is more electronegative than magnesium. So to indicate the delta positive and delta negative signs, we'll say that carbon is actually electron rich, and that the magnesium is electron poor, and the bromine is also electron rich. Here we have a trialcohol system in this molecule. And so we're going to first identify all of the polar covalent bonds. And so there are multiple in this one. So first we have oxygen, hydrogen, this one, and similar rules follow for these ones as well. We have one here, and we have one there. Great. So now let's determine the direction of the dipole for each of these 6 bonds. And they should all point, the dipoles should all point towards oxygen since it's the most electronegative atom. And it will look like this. And lastly, now we can assign the delta positive and delta negative signs. So since oxygen is most electronegative, it will bear the less delta negative sign. Excuse me. Here we go. So we have delta positive, delta negative, delta positive here, delta negative here. This is also delta positive, delta negative, and delta positive. And in this molecule, which is a ketone, let's define all of the polar covalent bonds. So we have only here, the only one we have here is actually just the double bonded carbon to the oxygen. So therefore, the direction of the dipole is going to go away from the carbon towards the oxygen, and therefore oxygen is delta negative, carbon is delta positive. And lastly, we have this molecule, CCl4, carbon tetrachloride. This is a common solvent used in organic reactions. And so all of these 4 bonds are going to be polar because carbon and chlorine have the greater than 0.5 but less than 1.7 electronegative difference. So all 4 bonds are polar, so I'm just going to start out by drawing the dipoles. They're all going to point away from carbon. And a key thing to know is that the previous molecules that I did were actually all polar, but this one's non-polar because in a tetrahedral molecule, if you remember from general chemistry, if all 4 bonds are the same and all the terminal atoms are the same, therefore all dipole moments by vector addition, superposition are going to zero out. But based on what the question asks, we're trying to draw the delta negative and delta positive signs. So all 4 chlorine are going to bear a delta negative sign, and the carbon bears a delta positive sign, and that's the answer. So now, I hope those exercises help with because inductive effects due to dipole is very important in a lot of things. It helps predict reactivity in organic reactions, knowing which one is nucleophile versus electrophile. And another big thing is that we're going to very soon look at acids and bases in organic chemistry. And a common type of exam questions that I see, especially from the top universities like Harvard, they often like to rank things, rank for acid from strongest to weakest, or weakest to strongest, and inductive effects is a huge component towards organic acids and bases. So on your own, it says that the regions of delta positive in a compound are the regions most likely to be attacked by an anion, such as a hydroxide. In the compound shown, identify the 2 carbon atoms that are most likely to be attacked by a hydroxide ion. So if you can now pause the video for a couple moments, for a couple minutes, and attempt this question on your own, and that would be great. Thank you. So when you're ready to go, this is the answer. So I didn't exactly draw it on here, but we're going to have a hydroxide attack on 2 carbons. And this is the Lewis dot structure for hydroxide. Now, which 2 carbons is it going to attack? I'll also label this 1, 2, 3, 4, and 5. The answer is going to be 2 and 5. And I'll show you why. So I'm going to clear the slide here. Now, hydroxides love to attack this carbon or this carbon. And the reason is that these 2 bonds are the most polar of them all. As a matter of fact, the only 2 polar bonds in this molecule. And with the dipole going in this way, the dipole going this way. So therefore, judging by the dipoles, we can say that the carbon here is delta positive, and this oxygen here is delta negative, as well as this chlorine is delta negative, and this carbon is delta positive. The rest of the carbons are not really much delta positive or not, so therefore these 2 carbons are the ones most likely to undergo a hydroxide attack. And as a matter of fact, you'll learn these 2 reactions very later on in the course of organic chemistry. So the hydroxide attack onto this carbonyl is known as a nucleophilic addition reaction, whereas the hydroxide attack onto the carbon bonded to chlorine is known as a substitution reaction. I won't draw the mechanism out here because this is not the time to discuss it, but this is just a brief intro to the future concepts. Hope this helps. And one last thing here is that there's another extra practice problem. Feel free to attempt it on your own. I don't post the answers to these ones. And if you have any questions, suggestions, here's my contact info. And I hope this session really helps with the importance of inductive effects and on drawing determining which atoms are delta positive and delta negative. Thank you.